تمام. Okay. Today's lecture we will start studying the performance of transmission line. This lecture is in chapter 10 from our reference book. So, as we know, in transmission line, we have three components: resistor, inductor, and a capacitor. Okay? Generally, we have to categorize transmission line into three types, based either on transmitting voltage or based on the distance. So we will have either short transmission lines, we will have short transmission line up to 50 kilometers when the transmitting voltage is less than 20 kilovolt. When we see transmitting voltage is less than 20 kilovolt, we will assume that it's a short transmission line, and then we will apply the rules of short transmission line. When the distance is between 50 and 150 kilometers, and the transmitting voltage is between 20 kilovolt and 100 kilovolt, we will have a medium transmission line. Other than that, we have long transmission line. Now, when we are analyzing our transmission lines, and when we want to study the performance of our transmission line, there are some terms that we have to understand, some important terms. First term is voltage regulation. Voltage regulation is giving us or is calculating the difference between the sending end voltage and the receiving end voltage. It means that gives us the percentage of voltage drop in the line. So always we want the voltage regulation to be as low as possible. It means that if we transmit 1 kilovolt, we want to receive 1 kilovolt. We don't want to have voltage drop in the line. Practically, we don't have voltage regulation equals 0. Always there is a voltage drop in the line. So voltage regulation equals to, this should be Vs, okay? Here it's VR, this should be Vs. Vs minus VR over R, which is a percentage, then we will multiply it by 100. Okay, we will multiply it by 100. So always we want to have a low voltage regulation in our transmission lines, but always remember, practically voltage regulation is always greater than 0. Okay. The other term is transmission efficiency. We know that when we calculate efficiency, it's receiving end power over sending end power, or P out over P in. In transmission line, and because we are working with AC systems, the receiving end power equals to VR IR cosine theta or phi R. Okay, this is power factor at the receiving end over sending end power, which is Vs Is cosine theta S. Cosine theta S is the sending end power factor. Okay, always we want transmission efficiency to be near 100%. Now, these are general terms that we are using with transmission lines. Now, if we have a short transmission line, we said we will have three components. We'll have three parameters: resistance, inductance, and capacitance. But due to the smaller length and low voltage, here you see voltage is less than 20 kilovolt. Due to this low voltage, the effect of capacitance is very small, and therefore it can be neglected when we are working with short transmission lines. Now, here, this is the sending end voltage, and this is the receiving end voltage. Okay, sending end voltage and receiving end voltage. If we draw the reference phasor diagram for the short transmission line, don't forget, you have to know how to draw the phasor diagram. It's very important. Now, if we have VR as a phasor, if we say phasor, it means we have a value and a direction. Okay, we have a value and direction. If we have VR and there is an arrow on it, it means this is a phasor. And when we say phasor, it means we have a value and a direction. So if the sending or the receiving end voltage VR is the reference, then there is an angle between sending end voltage and receiving end voltage. We call it alpha here. Okay, we call it alpha. And I, the current, is lagging, or the angle between current and the voltage is theta. Okay, current is lagging the voltage. So from here, if we want to calculate this Vs, sending end voltage, as a phasor, we say Vs equals to this Vr, okay, Vr plus this component, okay, plus this component, which is Iz. Z is the impedance. Okay, just 1 second. Okay, 1 second. So this is Iz. Now Vr as a component, Vr is equals to Vr. I, the current, is I multiplied by cosine theta r minus j sine theta r. Z impedance equals to r plus jxl. Okay, jxl. Okay, here, this is the final equation for calculating the sending end voltage. Okay, now IR and IXL are small component to BR, are small components to VR here. Okay, and here XL and IR are small components. We compare them with BR. Therefore, the second term can be neglected. Okay, the second term, this one, can be neglected because this value is very small. Okay, these values are very small values. Now, if this term is neglected, the square root will go with 2, and we will have VAS equals to VR plus IR cosine theta R plus IXL sine theta R. Okay, this is when we are dealing with short transmission lines. Now let me show you. Now you see this word, right?
Yes.
Okay, so this is a single phase short transmission line. You always have to know how to design the electrical circuit for your transmission line. If you know to design the electrical circuit, then you will remember the equations. Some equations then you don't have to memorize. Because, for example, this is Vs and this is Vr. Always, the voltage regulation is the difference, because always the voltage that we send is greater than the voltage we receive most of the times. Okay, most of the times in normal systems, voltage we send will be greater than this voltage. So a voltage regulation will be Vs minus VR over VR. These terms you have to know. I is the load current, R the resistance, loop resistance. If it's two-phase, for example, or if it's three-phase, we will say resistance per phase or total resistance, okay? XL is the reactance, don't forget. Who knows how we can calculate XL if it's not given from the example? How we can calculate XL?
1/2 pi FL.
1/2 pi.
Pi.
2 pi,
It's 2
2
pi.
pi FL.
2 pi
2
FL.
pi, 2 pi FL.
Yeah. XL is 2 pi FL. Frequency, if it's given, value of inductor is given, then you can find XL. Okay. So cosine theta R is the receiving end power factor, and cosine theta S is the sending end power factor. Okay. Now these equations we already discussed. Let's go back to our PDF. This, if we generalize the circuit and we generalize circuit constants of transmission, but I prefer using these equations instead of generalized circuits, okay? Because the probability of making a mistake is going to be less. Now, this is the voltage regulation. For lagging power factor, if we want to calculate voltage regulation, there it's going to be plus, while for leading power factor, we will use minus. General notes, for three-phase short transmission line, the calculation of one phase can be made in the same way as for single phase, okay? If we have short circuit transmission line, I mean short transmission line, three-phase, we will calculate phase by phase with using the same equations. Voltage regulation is positive for lagging power factor or unity. Voltage regulation is negative for if the load power factor is leading. Now, we know that power equals to VI cosine theta R. This is for single phase. Okay, power will equals to VI cosine theta R, and then we can find either V or I from the power equation. For three phase, we will multiply it by 3. For three phase, we multiply it by 3. Okay. Now, in medium transmission line, we have two methods to analyze our circuit. Okay, we have two methods that we are going to study, only those two methods for medium transmission line. It's called nominal T method, and the other method is called pi method. Okay, now this is the nominal T method. We draw our transmission line as letter T here and here. It means that we divide our resistance and reactance by 2. We have half of the resistance and inductance in this side, and then we will have the other half in this side, while the total value of capacitance will be in the middle. Okay, will be in the middle. You always have to know how to design. Okay. Now this is IS, this is IC, and this is IR. Okay, V1 is here and VR here. You have to study the phasor diagram as well. Now, from this phasor, always if we take VR as a reference phasor, okay, because VR as a phasor equals to VR as a magnitude plus 0. We don't have an imaginary part. We'll have only the magnitude. So V1 is the voltage that appears across the capacitance equals to, here, this V1 equals to VR plus this voltage plus the voltage here, okay, plus the voltage here. The voltage here equals to IR multiplied by this value, okay, Z over 2. R plus JXL is called Z. So you'll have Z over 2 here, half of the impedance in this side and half of the impedance in this side. So V1 will equals to VR plus IR multiplied by Z over 2, okay? Where Z over 2 is R over 2 plus JXL over 2. Now, IC, current across the capacitor, equals to V1, we already calculated, over ZC, this value, okay? And will equals to J omega C multiplied by V1 will equals to J omega C is Y, okay? This is for calculating IC. Now this is IS. IS will be divided into IC plus IR. Some current will go this direction and the other one will go to this direction. So IS will equals to IC plus IR. Okay, IS will equals to IC plus IR. We already calculated IC as this equation, and IR is easy to calculate. So we come to calculate VS, okay? VS, this is VS, all right. So from here we know that VS will equal, so if you put a voltmeter here and here, it will calculate V1 plus this current multiplied by this value. So VS will equals to V1 plus IS Z over 2. Okay? Equals to V1 plus IS Z over 2. What's the value for V1? Here we already calculated. VR plus IR Z over 2. VR plus IR Z over 2. Okay? Plus IS Z over 2. We already know IS is IC plus IR. So we substitute IC plus IR in the place of IS. So we get this final equation, okay? Now substituting all the equations, we will get the final equation for calculating VS is this one. And this is for IS. قال منن؟
بس
بس هيك بسيارني انت بيري واضحة؟ هابيليا واضحة؟ هابيل
بله سيدو.
اوكي هونات
بله سيدو.
نيروش
بله سيدو.
شنيان يا واضحة شنيان؟
بله سيدو.
Okay, let's continue. So these equations are very easy to memorize if you understand how to draw the circuit, okay? Now, this is for nominal T method. The other type or the other method is nominal pi method. Here, we will divide our capacitance into two capacitance, okay? So we will have as a shape of pi. We will have R plus X, JXL in the middle, and C over 2 on this side, C over 2 in this side. So we will have IL, IC over IC2, and IC1, okay? So this is phasor diagram. VS equals to, here, this is VS. VS equals to VR plus IS, okay? Plus IL multiplied by Z, this current, okay? This current. So VS equals to VR plus this voltage. IL here, if you look, IL becomes IC1 plus IR. IS equals to IC2 plus IL, okay? Now, if we substitute these equations, IL and IC1, you'll get VS equals to 1 plus YZ over 2 multiplied by VR plus ZIR, okay? ZIR. Now IS equals to IC2 plus IR plus IC1. Okay, this is the final equation for calculating the current. All the other equations for voltage regulations, sending and power factor, efficiency are the same. Now, the important point here, you have to know how to draw this one. And if you draw it, then you will know how to drive your equations, okay? Also, this is required from you. You have to know how to draw it. Let's go to our Word. So now here I will upload this one also for you on the model. I have just a second. Now, the final one is long transmission line, okay? Performance of long transmission line is more difficult than medium and short transmission line. So long transmission line is here, it's not required from you in the exam. Here it's for your informations. It's not required from you in the exams, okay? Because of your quiz, let's stop here. The final or next lecture, we will try to solve as much as possible from examples. So all these examples are homework from you. We maybe make us a quiz about these examples, so you have to study. Okay.
أسبوع عبد سيدة